Thank you for the invitation. It's my first time in Stony Brook, and people have been very welcoming. If you have any feedbacks or comments on my talk, please talk to me. I'd love to hear from you. Okay. Today I want to talk about special maps from Riemannian manifolds to metric spaces. And I want to talk about some applications. The goal of the talk is really to describe a basic philosophy. It's not going to be a set of rules that you can apply in different settings like a recipe, but it's going to be a vague idea that comes up again and again in very different settings. And it's the use of special maps from M to G. So let me set up the stage. As a geometer, I want to understand Riemannian manifolds, and it's going to be a smooth manifold that you can consider as, for now, as a closed, so compact without boundary, smooth manifold that you endowed with a Riemannian metric. Well, this is a Riemannian metric. What is a Riemannian metric? It's a scalar product at every point of M. And using this Riemannian metric, it's basically giving you the shape of your manifold. It enables you to measure length, volumes of regions, curvature, things like this. And you want to map it into a certain metric space. So a metric space is a more general notion. You have a topological space, and you put a metric on it. So a metric gives you the distance between any 2 points in this topological space. Just to clarify, if you have a Riemannian metric, you also know the distance between any 2 points in M with respect to that Riemannian metric. So a Riemann metric is a very special case of a general metric like this. And yeah, or I can allow infinite distances. Let's be generous. So this is the basic setup, and I want to consider special maps like this. What do I mean by special here? Essentially, I'm going to mean three things. Either isometric maps, or harmonic maps, or minimal maps. And I'm going to define those terms as they come up in the talk. All right, so let's start with isometric maps. Let's see. Okay, isometric embeddings. So those are basically embeddings that are going to respect the metric structures on both sides. If you start with something that's already embedded in a Euclidean space, then the Euclidean space has a canonical scalar product, so a Riemannian metric, and it induces, just by restriction, a Riemannian metric on this submanifold. So basically what I'm saying is that there is a trivial way to cook up metrics on M. You just look at an embedding in a Euclidean space that induces, by restriction, a so-called pullback Riemannian metric on M. So this is the very concrete and trivial way to get a metric on M. But now, if you start with an abstract Riemannian metric, the natural question is, can you realize it by a concrete metric? So now, given an, again, abstract Riemannian metric on M, can you find such a map such that the pullback metric is equal to our G that we care about? So is there any question on that question?
Oh, the K is fixed or maybe?
So here you allow K to depend on phi.
For people that haven't thought about the subject much, it's maybe you can point out that this is different from pulling back the distance function. Right?
That's right. I'm going to try to explain that point a little bit later. So maybe what I need to say here then is that this condition, what it means basically is that if you take any curve in M, so it has a certain length that you can measure using this Riemannian metric. Remember that this Riemannian metric enables you to measure length, volumes, curvature. So the length of this curve is going to be equal to the length that you can measure using using this embedding. So for any curve, you have this. Basically, this is what this equality is saying. All right, and so the answer is yes. And so you can find for any Riemannian manifold, say of dimension n, you can always find a certain k and a certain embedding such that if you pull back the metric, you get the Riemannian metric that you started with. And again, that's nice because it's saying that all the abstract Riemannian metrics that you can put on the manifold M are simply or equal to all the concrete metrics that you can obtain just by restricting the flat Euclidean metric in Euclidean space.
Is this true for each level of smoothness? Or you can forget that question.
So definitely the existence of such a thing is going to depend on smoothness. If you only, for example, care about C1 such maps, then in fact you can get much better case. Yeah. A much smaller case. Open manifolds. I think it's true, yeah. I think there's no problem here. Concrete metrics that you can obtain by restriction.
Situation.
I used to know, but I forgot. I think it's different. The analytic, maybe someone knows. I think it's.
So the local analytic. So even the local theory is complicated in the real analytic case, but I mean it still does go through pretty much the same way. I think you have to, the dimensions are higher.
Okay. Okay. Good to know. So we had a lot of questions, but then another question is whether or not such a phi is unique. In fact, it's highly non-unique. And so it makes this statement kind of useless. Before someone throws tomatoes at me, I want to explain what I mean by useless. So this theorem is a famous example of a theorem where the proof is much more interesting than the statement. The statement here is in such a way that you cannot really use such a phi for applications in geometry, whatever that means. However, the proof played a fundamental role in the development of geometry and analysis. But for today, we are interested in applications in geometry, so we're interested in more interesting isometric embeddings. So that's the next step.
Maybe sort of unique for embeddings of surfaces in 3 space.
Oh, but that's not in the realm that he's talking about, right? So it's, in the Nash argument, you're choosing a dimension large enough so that you have as many components of the metric. You're using all of those variables in the target space to make the components of the metric.
Nevertheless,
Yeah, that's right.
it's possibly unique. That's a famous problem.
Yeah, so if you, for say convex surfaces,
It doesn't always exist, but it is unique.
yeah, for convex surfaces, it's going to be unique. For surfaces, embeddings of surfaces in R3 that are isometric. But in general, it's not going to be unique, even for R3. Yeah, because say you have a dent and you reverse that dent, but the rest of the surface is the same, you can do that in such a way that both are isometric embeddings of the same Riemannian surface in R3. But
Annulus between.
yeah, it's a flat annulus here.
Oh,
Yeah.
I didn't know that.
Convexity is important.
Yeah.
I think the question is the continuous isometric deformations. That's conjectured to be
Oh,
continuously deformed isometric.
I see.
What was the comment?
That you, once you're given one isometric immersion, say, you cannot deform it through,
Yeah, that's-
non-trivially through.
That's one version of the question, but this is already interesting.
For complete surfaces, it's quite interesting that the lack of you have these classic things for minimal surfaces where you can bend them without.
Yeah, yeah. All right, so this is Riemannian isometries. I want to talk about metric global isometries. So where's the eraser? Sure. So, and I want to emphasize that global isometries are something different from Riemannian isometries. So you can ask, whether or not there exists an embedding of M with the given metric to a high dimensional Euclidean space which is globally isometric in the following sense. So you have that the distance function is sent to the distance function. Let me, for those who are not familiar with that, let me give you a picture to see what can go wrong. So let's suppose you're interested in the usual. Yeah. Yeah, exactly. So let's pretend we didn't hear that, and let's look at the usual round S1. So this is a circle, but you have to think of it as just an abstract manifold with an abstract Riemannian metric. And S1, you can embed it in the standard way. in R2, right? So here, this is the abstract S1. Let me give you 2 points. And it's mapped inside R2. And the claim is that this is not a global isometry. It's a isometry in the previous sense because infinitesimally the distances are not going to be changed, but globally the distances are going to be changed because if you look at everything inside the world of the circle, the distance between A and B is, say, pi, because you have to travel around the circle itself. Nevertheless, if you are inside R2 with the usual distance in R2, the distance between the images is just 2, right? Any questions? So, let's see. So the answer to the question is no. It's never possible. At least, again, you're considering M, which is compact and closed, so boundaryless, so compact. It's an exercise that you can try to show. The interesting thing is that the answer becomes yes when you replace Euclidean space by some Banach space. And in fact, this kind of property is very easy to prove, contrarily to Nash's theorem, which is pretty heavy. This thing is really a simple construction due to, I think, Kuratowski, which says that any, say, compact Riemannian manifold can be embedded globally isometrically. One observation here is that this kind of idea that you want to embed things into a function space is going to come up later. The proof is the following. So I'm going to call this phi k. And it maps any point in M to basically the distance to x. Okay, so this is a function of y for any fixed x. Y is in M. And this is, as you can check, a bounded function on M. And let's check that this is an isometry. For any 2 points in M, you're going to get 2 functions, and you want to know the supremum norm of the difference. So let's go. Well, by definition, You have that, and well, let's see. If y is equal to x1 or x2, you get that this quantity is exactly the distance between x1 and x2. And in fact, using the triangle inequality.
I don't understand. What do you mean the sup over GG is fixed?
This. Oh, yeah, y. Sorry. So y. Yep. And questions? So again, you have 2 points, x1 and x2, and you have two functions that depend on so the y variable. Okay. So you want to take the supremum of this function, and what I'm saying is that if you take y to be either x1 or x2, one of those quantities is 0, and so this is going to be equal to the distance between x1 and x2. But we're interested in the supremum. However, I don't really have time to explain why, but there's something called the triangle inequality that's well, it's a colloquium. It's a colloquium, right? So it's exactly the distance between x1 and x2. And so it's a global isometry. And the first time I saw that, I was really surprised.
Yeah, I'm still.
Yeah, me too. As you can see, the proof is, once you know what to prove, it's very easy. But this map is quite canonical. Once you fix the metric, basically you have this canonical embedding of Kuratowski.
Is it a unique global isometry?
No, it's not. You can cook up weird isometries, but I don't have an example in mind. Let's see. So here the remark is that this particular phi k is quite canonical, and it makes it very useful. All right, so that's it for the introduction for isometric maps. I want to talk about another kind of special maps called harmonic maps. And I'm going to be a little bit vague here, but so let's consider, again, the same Riemannian manifold and a map into some Euclidean space with the standard metric, and you map it to psi x, which is equal to the coordinates here. All right. So you say that this map is harmonic basically if each coordinate function is a harmonic function on M. Okay, so here the delta is the Laplacian on M. Basically a sum of second derivatives. And you can generalize that notion of harmonic maps when you replace this manifold by a more general Riemannian manifold. So here, maybe you can allow, it's better to allow the boundary to be non-empty.
Not empty, not zero.
Oh, yeah.
generalize it? Because I don't know what the Laplacian of the map is.
Yeah, so
Is it into Rn?
If it's into a submanifold of Rn, then the condition is that the Laplacian is everywhere perpendicular. So the Laplacian of the map would be a vector. And then you ask, that has to be perpendicular to the submanifold. But it comes out of wonderful variational bound.
that's right. Or you can say that a harmonic map is a map that is a critical point of a certain energy that you define by taking the norm of your differential square. So it's really like harmonic functions. They're going to be critical point of that energy. You have a way to measure the norm of the differential of a map between two manifolds.
But given that definition, I wouldn't know why it agrees with the
Yeah, so
Euclidean space.
well, so if you do have that, you are a critical point. So here you have some metric to put here. It's basically an integration by part.
Okay.
So it's I claim that it's really similar to the situation for our harmonic functions. Harmonic functions are known to be critical point of that Rayleigh energy. So you see that this is, again, a notion that depends on the metric G, but it's very far from being a metric notion. It's very far from potentially preserving distances, for example. It has nothing to do with that. It's a PDE that you have to be satisfied. You know? And just another remark. So here I'm going to consider harmonic maps into, say, Rm. If you've heard of the Dirichlet problem, the Dirichlet problem is just finding a harmonic map into R. So a harmonic map into R is just a harmonic function. That's it for harmonic maps, and let me mention what I mean by minimal maps. So if you now look at, a general map from a manifold to another manifold, you can, for the purpose of this talk, for the purpose of this talk, I'm going to define minimal by being both harmonic and isometric, a Riemannian isometric. Minimal. Just for the sake of simplicity, let me use this as a kind of definition of the word minimal.
So there are contexts where it's actually harmonic and formal rather than isometric.
That's right. That's right.
Quotation marks. You have to wait for a lot.
Yeah. And I'm not going to say much more about minimal, but let me give you an example of what I mean by a minimal map. So suppose...
What does the plus sign mean?
And, like, is that one there? So let's assume that you have a map so again, with the respective Riemannian metrics. So M is maybe this manifold with boundary. You map it somewhere. So you're looking at the image of M. And let's assume you have this Riemannian isometric embedding. So let's assume that. And let's assume that for any map phi prime homotopic to phi, such that the boundary of phi m is equal to the boundary of phi prime m. So let's assume that this implies that the volume phi m of volume of phi m is less or equal than the volume of the image of m by phi prime. So let's assume that. Then you have a minimal map, okay? Then phi is minimal.
You had a manifold boundary?
Yeah, so let me finish the picture. So this is the given manifold with boundary. You isometrically embed M. And let's assume that whenever you deform phi continuously, but still preserving this boundary condition, you get so another embedding of M. This is phi prime of M. And we're assuming that for any such phi prime, the volume inside N, the ambient space, the volume of this phi prime M is larger or equal than the volume of M. So if that is true, then M is phi is by definition minimal.
Theorem. This is a different definition.
Yeah. Well, I'll just add theorem. Yeah, I mean, it is going to be. It's Riemannian isometric, and you have this volume condition, so you're minimal. In fact, you are harmonic. Let's move on. No, they're not equivalent.
Okay, but the first, it implies that we have minimality.
That one implies this, that example.
It also implies minimality by any definition, but it's stronger. It's like stable minimality.
Yeah, it's minimizing minimality.
But this definition here, the general definition involves a critical point, involves a minimal.
That's right, that's a good point. So in this example, this is a minimal point of the area or the energy here.
Well, I see, you're including these into the...
Yeah, this is a particular case of minimal embeddings. Let me finish with minimal maps. So minimal maps, again, are at the intersection of harmonic maps and Riemannian isometries. Riemannian isometries are about really purely the metric, but harmonic maps are more about satisfying a PDE. So minimal is really special even compared to isometric and harmonic. Okay. Now I think I can move on to some applications.
This makes sense for closed manifolds, right? It's general definition minimal.
But when you look at the variational problem, wait, compactness according
So here, I don't think you need compactness because, well, Riemannian isometric, that's fine. And harmonic, you can define it locally. You can recognize that a map is harmonic just by looking at neighborhoods. And if in each neighborhood you are harmonic, then you satisfy this PDE.
I asked for closed manifolds.
So it also makes sense for closed manifolds. Oh, interesting examples, I see.
No, well, I'm just worried about all the definitions. If you took minimum, the minimum critical points just had no boundary conditions, it'd just be the point map.
That's right.
Here.
That's right.
But then I asked, are there non-trivial examples?
Yeah. So here you want to. That's right. You want to not minimize over all possible maps from say S1 to the surface, but just say fixed in a homotopy class. So if you fix the homotopy class, then in that homotopy class you can minimize the energy. You will get a non-trivial map.
Now, I was wondering about a closed manifold mapping in the Euclidean space.
Euclidean space, that's a good point. There's no such maps. There's no such maps, and it has to do with the fact that there's no non-trivial harmonic functions on the closed manifold. Yeah.
Well, maybe that's your picture points out an important example, right? So any geodesic or closed geodesic is a harmonic map of a circle into a harmonic map.
That's right. Yeah. Yeah. So a geodesic is an example of a minimal map from the circle. Let's see. So what can we say using this notion of isometric embeddings? Again, I'm going to be more interested in global isometries. One thing that you can do is to compare different Riemannian manifolds. So you have two, say, compact Riemannian manifolds. And a priori, it's non-trivial to try to compare them because they are just abstract spaces with different underlying spaces with different metrics. So how do you even compare the shape of those two manifolds? Well, so the idea is that you want to embed them in a common space in which comparing them is easy. So there's something called the Gromov-Hausdorff topology that does exactly this. So you say that those two manifolds are epsilon closed in that topology. In PH topology. If you have global isometries, into a common Banach space, such that in this particular Banach space, the images are epsilon closed in the so-called Hausdorff topology. And that just means that for any, so it just means that the images are really visually close to each other, right? So you put your two manifolds into one ambient space, and then in this ambient space you can talk about distances. So J1. So you have that the images are closed in a pretty natural way. 1, 1. So this is one way to compare manifolds. Let me quickly mention another way to tell you that really this is a principle that seems simple, but it came rather recently. I mean, it's basically due to Gromov, so it's not that ancient. This is not the only natural way to compare two manifolds. So let me mention that there's this Gromov-Prokhorov topology, which is almost the same, except that at the end, so you say that you're epsilon closed in that new topology if you have such global isometries, such that the images are going to be closed in the measure sense. So as measures, they are closed. So same thing, except those last lines. So you can define what you mean by epsilon closed as measures if you are already in one space as measures. In the Banach space B. Any questions?
The measure is pushing forward the Riemannian measure?
That's right. Looking at push forward of the usual Riemannian measures.
Why does it follow?
It does not. So these are independent topologies.
Why does it follow from this definition that the measures are close?
It might be that it could be very, very rough maps, right?
Yeah, so if you have, say, a circle that's somehow mapped isometrically in that Banach space like this, and you have another circle that's mapped like this, so from the distance perspective, really this is the same thing almost. But from a measure perspective, this has much more length concentrating around that point. So those two, none of them imply the other. Yeah, on the contrary, you can be closed, of course, as measures, even though you have some small volume sets that are very far away. So that's nice. With this notion of global isometries, you can compare manifolds. You can also formulate very powerful compactness theorems. And I want to mention one because it's, I think it's a remarkable theorem. So let me say you can get compactness theorems. So this is, I think, another application, which is due to Wenger. And it tells you that, so you have a sequence of abstract Riemannian manifolds, and you would like to say, well, subsequently that converges to something. It's really hard to make sense of that sentence. So the statement here is saying that if you are putting those mild assumptions, so first, a uniform diameter bound, and second, a uniform volume bound. So if you have such a sequence, then in fact you have something converging. So there exists phi I. Banach. So you are globally, again, isometric. And the images are going to converge to something in a measure sense. That's pretty surprising to me that you can do that subsequently. As measures, so what is this limit? This limit is definitely not going to be a submanifold of B in general, but it's going to be something with some almost smooth structure. Is going to be a countable union of Lipschitz submanifolds of B. You can make sense of that sentence. Lipschitz.
And the fact that the ball is not compact does not create a problem for this kind of statements?
Yeah, so here you really need to choose those embeddings well. You can imagine that if you choose, of course, your embeddings badly, then they're going to escape at infinity, even if they're in a bounded set. But if you somehow choose the right isometries, you can make sure that they're going to converge to something in a reasonable sense. Lipschitz submanifolds. Anyway, this is something I wanted to mention because it's not so well known, but it's very useful because the limit is not some random measure. It's in fact coming from.
What is the symbol C infinity mean?
It's the notation of people in the field, but it's a current. it's a current in the sense of geometric measure theory. So usually people use this letter. So those are some, I think, interesting application of the notion of isometric embeddings. Let's see, without proofs, some very nice applications of this notion of minimal embedding. Embeddings. And so let me give you a statement and a conjecture. So consider an n-dimensional open set, which is relatively compact. So open, but like bounded in Rn with the Euclidean metric. Now, let's put another abstract Riemannian metric on this omega. So let's put G on omega such that you have the following condition. For any x and y on the boundary of this omega, you have the following inequality. So you have to imagine that so you're only allowed to compare the distances for points on the boundary of omega. And you're assuming this comparison. The conclusion is that you get information on the interior of omega for the respective metrics. What you get is that the volume with respect to G is in fact larger than the volume with respect to G Euclidean. And the basic idea behind the proof, which is due to Gromov, is, I just want to write one sentence, it's that you embed this into a Banach space. For example, this one works as a minimal map. So find an embedding that is a minimal map. Actually, the standard embedding, you want to show it's a minimal map. Using minimality in this ambient space, you can deduce something, a comparison for the volume of the manifolds before taking this embedding, which I think it's
The standard embedding is a minimal map.
That's right, in the sense that I described in the example, meaning any other map is going to have larger area for the same boundary conditions. So you have to imagine that, yeah, so omega is here, you're embedded into L infinity, and any other region satisfying this can be mapped to some weird region in L infinity, but with the same boundary condition. But since you showed that this is minimal, it will have less volume. And with some work, you can deduce this thing. Okay, I really didn't have time to talk about what I wanted to say, but let me maybe mention a conjecture, because I have zero contribution on that conjecture, but it's a very intriguing conjecture that says the following. So let's look at the hemisphere, all right? So this is the hemisphere of dimension 2, the round one. It has boundary S1. Now let's look at another surface gamma with the same boundary S1. So gamma is another Riemannian surface with some boundary, and suppose that you compare the distances G round. So conjecturally you have that the area of omega for G is at least the area of S2 for the round metric. So first time I saw that, I couldn't believe it was still a conjecture, but after 2 weeks of trying, I realized, I had to admit I didn't understand this conjecture, and I had to move on.
You have two P's in soup.
Oh, sorry?
What's that soup?
Suppose, yeah.
Suppose. Distance.
Suppose that
Why the boundary, the distance?
for any point.
Word with hypothesis.
Yeah. So let's see. So you have two surfaces with the same boundary, which is an S1.
Got that.
And you take 2 points. You can measure the distance between those 2 points in that manifold using the round metric, or in this manifold using this metric G. And the condition is that the metric G is going to dominate the round metric.
Then,
So this is about local isometric embedding of the circle in the circle, rather than, it's not just a Riemannian embedding, right? So otherwise you get counterexamples immediately, but.
So yeah. So it's really the distance as Riemannian distances for the Riemannian manifolds, right? So you look at all the curves from X to Y, you take the shortest curve, and you look at its length.
is that an equator?
You can think of it as an equator, yes.
So the distance is along the equator?
Exactly.
No shortcuts.
That's right.
I see. This is a thing with no shortcuts, then its area is bigger.
Yeah.
This is the smallest thing with the thing with no shortcuts.
Yeah.
Okay.
And so many people tried, the basic strategy is people try to find tricky and smart embeddings of those things in the common space where we can kind of compare them and use this minimal embedding idea. It's not clear it's the right strategy, but it is one of the most promising strategies. So let me finish by saying at least 2 words on what I wanted to mention, because you have similar applications for
That's why the Earth is like that.
yeah. Similar things for harmonic maps. Let me quickly mention that you have something called the positive mass theorem.
There's no assumption this is embedded in R3 or anything.
No. It's just abstract surfaces.
Right.
Abstract surfaces. But even for embedded surfaces in R3, people cannot prove that. It's only known when you know something about the topology of gamma. If you know that gamma is a spherical region.
Disk.
So genus 0.
Disk.
Yeah, a disk.
Metric characterization, this nice thing that we all know and love. Fantastic.
Yeah. So let me give you what I want to say. So the positive mass theorem is a result in general relativity, and it's a result of Shen and Yao. And many other people contributed within many new proofs of this theorem. I want to mention the proof that one proof that uses this idea of harmonic maps. So this is the one that I'm going to be interested in. So many proofs including one by Bray, Cazares, Marcus Curie, and Stern, Daniel Stern. So they use harmonic maps theorem, harmonic maps techniques to reprove this major theorem, and there was a conjecture about the stability of such a theorem, and I just wanted to say that with Tonghan Dong, who's a graduate student, where is he? There he is. We proved a stable version of that positive mass theorem. So let me just write this in words. The positive mass theorem is, in some sense, stable. And again, stability is going to be proved using this notion of first mapping into a nice space using harmonic maps. I'm going to stop here. So thank you.